same scale factor. And that's really the same context that we talked about when we were talking about congruency for the first time. In order to, before we knew anything about congruent shapes, and like angle, side angle, and side, 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 and that stuff, if I wanted to show two triangles congruent, I need to show three angles congruent to three angles, and three corresponding sides congruent to three corresponding sides. I need to show 6 things. We found out that that was kind of a tedious process. It could be done sometimes, but sometimes it was impossible. Same thing happens with similarity. Okay, if I want to show right now triangles similar, the way you have to do it is you have to show all 3 corresponding angles congruent and all 3 sets of corresponding sides proportional. Okay? 7.3 allows us to minimize that. We've got some statements here, some theorems, postulates that are going to allow us to cut our work down substantially. Okay? The first one will be called AA similarity. Okay? What do you think AA stands for? Angle, angle. Okay? So don't write this down, but it says we can prove that 2 triangles are similar, showing that all 3 corresponding angles are congruent and all 3 sides are in proportion to one another. And that's what we just talked about. Same thing for all other polygons as well. Okay? But there are simpler methods to prove triangles similar. Here's a postulate. Okay? Can't prove this to you. I can't give you the step-by-step reason for this. Well, I can demonstrate some images for you. But it says if 2 angles of one triangle are congruent to 2 angles of another triangle, so there's your AA part, then the triangles are similar. Okay? Then the triangles are similar. And what that does for us is it allows us to generate similarity without ever having to deal with the proportional side lines. Okay, so I can know now that 2 shapes are similar without, or 2 triangles are similar without ever having to deal with lengths. Sometimes, and I'll just put it in parentheses here, sometimes textbooks will call it AAA because of the third angles theorem, which says if 2 angles of one triangle are congruent to 2 angles of another triangle, then all 3 angles are congruent, right? So based on the triangle angle sum theorem, we know there should be 180 degrees in this triangle, there should be 180 degrees in that triangle, and if P and Q are the same total as S and T, then that means R and U have to be the same angle as well. They have to be congruent too. Okay? So you might see it written as angle, angle, angle. All right, so to demonstrate this, I've got 2 triangles here, okay? ABC and A prime, B prime, C prime, okay? If I take, so I can, by moving this smaller triangle, by moving the blue triangle, it'll move the red triangle. But by doing this, if I move point A down to the origin, you see that that red triangle lands right on top of it, right? So do you guys agree that A and A prime based on that relationship, are congruent angles. Okay, so you got angle, angle there, or an angle congruent to an angle. Now I'm going to do the same thing for C. See if I can get them to match up. Okay, so C and C prime would be congruent, right? So that right there tells me that those two triangles are similar. Okay, so if those two triangles are similar, what we would say is triangle ABC is similar to triangle A prime, B prime, C prime. Okay, we know that now by angle, angle, right? But just like congruency, if we were able to show that triangles were congruent by like side, 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 then there was a conclusion to that. It said not only are the angles or the triangles congruent, but the parts that we haven't talked about yet in defining the shapes to be congruent, those parts are congruent. So what I mean by this is we've shown that the triangles are similar, but we only use the component of congruent angles to do that. So then what we benefit from this is things that we haven't talked about. We haven't talked about AB's length compared to A prime, B prime's length. We never had to do that comparison for this setup, this problem. But we now know that AB over A prime, B prime should be equivalent to BC over B prime, C prime. Should be equivalent to AC over A prime, C prime. That's kind of a, you guys remember CP, CTC, right? Okay, corresponding parts of congruent triangles are congruent. We could have something like corresponding parts of similar triangles are proportional. Okay, we don't have a phrase like that. Nobody's ever written that in a textbook, but it's the result of saying that these shapes are similar. And we can prove that algebraically here by taking, so when I say AB compared to A prime, B prime, that's talking about the segment C and C prime. So let me take, I'll take C divided by C prime, and it gives me 1/3. So the way I divided that, when I took this number here, that length, divided by that length, and they're in a 1-to-3 relationship. Does that make sense? Okay. Now, if I do the same thing with B, which is this distance AC, so take looking at this last ratio here, if I compare AC to A prime, C prime, if the shapes were similar, we should yield the same ratio of 1-to-3. And we're going to do the same thing for A compared to A prime. Still get the 1-to-3. Different values being divided, right? There it's C and C prime, B and B prime, here A and A prime. Different values being divided. And the values obviously then are, like I'm dividing these things here. So divide those two, and they're in a 1-to-3 relationship. Okay? Divide those two, they're in a 1-to-3 relationship. Divide those two, 1-to-3 relationship. Does that kind of make sense? So that proportionality is a byproduct of angle-angle similarity. Okay? So we can use that. Are these to find missing values? Are these two triangles similar? Yes, they're similar by angle-angle, right? Okay. So what I'm going to do is I'm going to write a similarity statement for this first triangle. So I'm just going to name it DFE. And again, that doesn't matter the order of the first one. But if I name that first one DF, that means down here I need to go from A to C. Okay? And this might be a question where some of you say, Fed, just go x over 45 equals 3 over 15. Okay, I think a lot of us probably see that that's the relationship that we're going to need. But in other problems, when the pictures are distorted a little bit more, rotated, flipped, that kind of thing, that's not safe. So I'm just going to I'm going to write the conclusion that I get from this similarity. DF should compare to AC, just like FE compares to CB, just like DE compares to AB. And that's exactly the same thing that we were doing in section 7.2. And now I know 4 of these things, 4 of these 6 components. So I'm going to go fill those in. DE, they tell me is X. FE was 3. AB was 45. And CB is 15. So it looks like I don't know anything about those 2 things. But when I do that, it's an extended ratio. And now I filled in, this was an extended ratio, extended proportion, I guess. I fill those in, and I get down to this right here, correct? Okay. My suggestion, maybe you want to do some simplification first. You when I multiply 5 times x, I get 5x. 1 times 45 is 45. X is 9. And that should make sense. 3 compared to 15 reduces to 1/5, right? 9 compared to 45 also reduces to 1/5. You should be able to check yourselves real quick once you find those initial values for x. Questions on that? Let's do this one. Okay. First question is, are they similar? Because there's no notation for the angles here. Okay. So first thing we have to do is, from previous 6 chapters of knowledge, are these 2 triangles similar? Okay. What can you tell me about that angle in comparison to that angle? They're vertical angles, right? Vertical angles are congruent, so we got that. What do these arrows and these lines mean? Say again? Parallel. If we have parallel lines, and I'm just going to look at maybe that transversal AD, what does that tell you about angle A compared to angle D? They're congruent, right? They're alternate interior angles, right? Does that make sense? Okay. Now you could have gained the same knowledge in this image, at least, by covering up that transversal and saying that B and C were congruent because they're alternate interior, right? Okay. Regardless, though, once I identify one set to be congruent, I arrive at angle, which ultimately tells me the other set would have been congruent as well. So you get that. Okay? So they are congruent by angle, or not congruent, similar by angle. And now let's name them. What do you want to name this triangle on the left? AB? So since you started at A, you need to start where over here? D. Okay? And then you went to B, so then here you got to go to C, right? And those then are the 3 ratios that you get from that similarity. And I know what a lot of people might be saying, and it's just because of the structure of these examples that I knew I needed to put 2 compared to 5 here, and x minus 1 compared to x plus 5. But on a test or quiz, I'm going to give you all 3 segments of one triangle and all 3 segments of the other triangle, and I'm going to make it a lot more difficult to where you have to the orientation of the picture, you'll have to be able to use that. Does that kind of make sense? Okay? And the reason I want you to be able to do that is when we get down to chapter 8, you guys know on your calculator there's an SIN button, a COS button, and a TAN button, right? Sine, cosine, and tangent. We're going to use those. You guys do that at all in algebra last year? Did you use it at all in 8th grade or anything like that? Okay. So sine, cosine, and tangent are going to be the ratios for right triangles. Okay. Basically what it says is that every right triangle, let's say if it has a 30-degree angle in it, every right triangle, no matter how big it is, whether it's the size of a piece of paper or the size of the tri-state area, if it has a right angle and a 30-degree angle in it, the opposite side divided by the adjacent side is always going to be the same ratio. Okay? In order to understand that, we need to be able to do this right here. Okay? So that's why kind of right now I'm trying to focus and force us to write these out. Even though, like I said, a lot of us could probably circumvent this and go straight to 2/5 over x minus 1 or equals x minus 1 over x plus 5. Okay? But when you circumvent this, you don't pick up everything that you need. Does that make sense? And that's again going back to the idea, if we go straight to the homework before watching a video, yeah, you might get knowledge about that homework, you might get some of the things that we need, but a lot of times the homework doesn't force you to do that. Okay, and we need that. Okay, so plugging in these things, I know AB 2, CD 5, BE. So I don't know that ratio BE and CE, but I do know AE x minus 1 and DE x plus 5. This one is a little bit easier than the ones that you saw in that 7.1 worksheet because of where the binomials occur. If the binomials are both in extremes or if they're both in means, you'll probably have to factor, right? But if the binomials are just in one ratio, then you're going to end up with something that's linear. So I have 2 x plus 5 and 5 times x minus 1. Okay, so eventually you guys will get, I'll let you guys do that math, but it eventually gets you down to x equals 5. And let's just go back and check. If x is 5, what is that number right there? 4. And what's that number there? 10. What's 4/10 reduced to? 2/5, right? Or if you don't want to reduce, because reduction involves division, right? Yeah, cross multiply. A lot of people don't like to divide. If I have a choice of standing or sitting, I'm going to sit, right? If I have a chance of multiply or divide, I'm going to multiply. I'm just going to choose. Inherently, people are lazy, so I'm going to choose the easier thing, right? I'd multiply that number and that number, get 20. That number and that number, get 20. And that tells me that I have the right answer. Okay? All right, this one's a little bit more difficult. That's the last one we do today. What do you know about these two horizontal segments? They're parallel. So what does that tell you about that angle compared to that angle? They're equal, okay? Corresponding, right? Okay, corresponding angles are congruent if the lines are parallel. And you can do the same thing maybe with that set there and that set there, right? So you got angle, angle, okay? Is angle A also congruent to angle A? Can I see how that's, there's two triangles here that are overlapping at A. So we've got that going. So we can look at any grouping of those angles and we have angle similarity, okay? Now, what I prefer to do, and I think this is the safest thing, you don't have to do this. You can leave the picture completely alone, but I think it makes sense to take A, E, B, and A, D, C, and separate them. And we knew A was in both of them. We know E and D were corresponding. So when I name these, we'll say triangle A, E, B, and triangle A, D, C. Okay? But the reason I like to separate them is to kind of open my eyes, I think, a little bit better to the values that belong on those particular segments. I think it's easy to see that that distance AD is 8, right? What's AE? AE is 3. That's a segment for some reason. In my past experience, people miss that quite a bit. Okay? What's AB? X plus 2. What's A to C? X plus 2 plus 6, which would be X plus 8. All right, so a lot of times you might not, especially when your images are overlapping like this, they're not going to explicitly give you all the dimensions. You might have to do a little bit of just segment addition there. In this case, to find this 3, we did segment subtraction, but. So now, I think you guys could probably see, and this is one of those where I can compare left to left, right to right, that kind of thing. But the reason I can say 3 compares to 8 is because 3 was from AE and 8 was from AD. First 2 letters here, first 2 letters there. EB, which we don't know that length, should match to DC, which also we don't know that length. And the last one should be AB compares to AC, which we do know those. AB, X plus 2, AC, X plus 8. Cross multiplying, we get 3x plus 24 equals 8x plus 16. 5x ends up equaling 8. X then is equal to 8/5. Okay. Which, because it ends in a fifth, so that's 1. And 3/5, 3/5 is 6, so actually equal sign 1.6. And you can check that, you can plug that back in. And you'll get, what, 3.6 divided by 9.6. Should end up giving me the same thing as 3/8. So that's something we can do. Do you see how this is kind of a, I think actually 7/2 is a much more complex situation because we got more sides. We got larger extended ratios, okay? 7/3 kind of narrows the focus. Only going to be working with triangles. Only going to be working with 3 ratios. But it's really doing the exact same thing. Okay, but angle-angle similarity is that first postulate. Tomorrow, we'll get into side, angle, side, and side, side, side. Okay, I'll talk about those 2 things tomorrow. I will open up 7.3. It's not going to be due. It'll be due probably at least by Tuesday, if not later. And tomorrow, I should probably retract my statement. We will not get through both those things tomorrow because we got the. Oh no, you guys got an hour tomorrow. I keep forgetting that. We'll get through both of them tomorrow.